Okay, this is our second lesson on the sun and its energy, and this one focuses on electromagnetic radiation, which are electric and magnetic disturbances that travel through space as waves. Okay, this includes radio waves, microwaves, infrared energy, visible light, ultraviolet radiation, X-rays, and gamma rays. Right, all these forms of radiation are produced by the sun. All right, and we organize all these forms of radiation into what we call the electromagnetic spectrum. Okay. Now, these waves are invisible, right? But if we could see them, we would see these bumps here, like these crests, as we call the ones that are going up like this, and troughs, as we call the ones that are going down like this. Okay. So when we're talking about wavelength, we're talking about the measurement of crest to crest or trough to trough. Okay, that's what a wavelength is. Okay, so some of these forms of radiation have a long wavelength. You've got a really long space between crest and crest, or they have short wavelengths. Okay, which means just a little spaces between crest and crest, right, or trough and trough. Right, so all this energy, like I said, we organize into the electromagnetic spectrum. Okay. The farther you are to the left side of this diagram, the longer the wavelengths are. Okay. Farther to the right you are on this diagram, the shorter the wavelengths are. All right. Now, the longer wavelengths carry less energy and are less dangerous to us, humans and other living things. All right. The forms of energy with the shorter wavelengths, they're more dangerous. They carry more energy and they're more dangerous to us and other forms of life. Okay. So you can see the types of waves here. And a lot of times our technologies that we have are named after these different types of waves. Okay. Like you've got radio waves. Okay. AM radio is very long wavelength. Okay. Then you have FM radio, which is also long wavelength, but not quite as long. Microwave energy, radar. Okay. Now as we go to the right here, all right, we're starting to get more energy, okay? All right, we got a light bulb. All right, here's the visible energy part, okay? Or the visible light energy part. So this is where all the colors we have come from. Right? That's the visible light we can see, all right? All right, so then when we get over on this side, we're starting to get into the dangerous types of energy. They have shorter wavelengths, carry a lot more energy, and they're dangerous. They're more dangerous to us, okay? Like ultraviolet radiation is dangerous to all living things, okay? X-rays and gamma rays are very, very harmful. All right, so again, the longer the wavelength, all right, the less energy the form of radiation carries. The shorter the wavelength, the more energy that form of radiation carries. Now, here's another thing to point out. Doesn't matter how much energy they have, the long wavelengths or the short wavelengths, all of these travel from the sun through space at the speed of light. Okay, so regardless of the fact that the longer wavelengths have less energy and the shorter wavelengths have more energy, all these forms of energy travel at the speed of light. All right, Earth's protective atmosphere. So Earth has this protective atmosphere that protects us from lots of forms of electromagnetic radiation. Okay, we have the ozone layer, which blocks ultraviolet radiation, which is harmful to all living things, like I was saying earlier. We also have water vapor and carbon dioxide that reflect or absorb the other types of harmful electromagnetic radiation. So without our atmosphere, we would be way more subject to these forms of radiation and would not be able to survive here on planet Earth. All right, furthermore, the sun emits what we call a solar wind. Okay, this is a supersonic plasma of charged particles that flows outward from the sun at high speeds, and it bathes every planet and everything that it comes in contact with in these high energy particles. Okay, so considering this, how do we survive on planet Earth? Why are we not getting burned up by this extreme form of energy that's washing over us? The answer to that is Earth's magnetic field. Okay, the Earth has a magnetic field because the outer layers of the Earth rotate at a little bit different speed than the inner parts, the inner layers of the Earth, some of the inner layers. And it creates this magnetic field, which actually protects us from that solar wind. It deflects the particles and traps them in these two huge rings called the Van Allen belts, which you can see in our diagrams here. So that's why we are not burned up by the solar wind. All right, so you may have seen from where we live in North Carolina, you're not going to be able to see this, but maybe you've visited a place that's at a higher latitude, or you've seen a video or pictures of these really fantastic looking streaks of energy and light across the sky that you tend to see at the higher latitudes, called the aurora borealis or the northern lights. Right? This is how they are created. Okay, we said all those high energy particles are trapped in the Van Allen belts, and in there they collide with gases in Earth's atmosphere and give off this light that we call the auroras or the northern lights. So just a cool explanation of why, if you ever visit a high latitude area, you may witness this at night. You may witness this phenomenon at night. All right, the sun's energy reaches the Earth by the process of radiation. That's why we're calling these forms of energy electromagnetic radiation. Okay, radiation is simply the transfer of energy through space by electromagnetic waves. You do not need what is called a medium. When we're talking about energy transfer and we refer to a medium, we're talking about something physical that the energy has to travel through. Okay? So with radiation, you do not need a medium. Okay? Radiation can travel through open space, the void of space. It doesn't need anything to travel through. All right, what happens to the sun's energy? Okay, out of all that incoming solar radiation, different things happen to it. About 6% is reflected by the atmosphere, 20% is reflected by the clouds, roughly 4% is reflected from Earth's surface. All right, 51% is absorbed at the surface of the Earth, and then the remaining 19% is absorbed by atmosphere and clouds. All right, let's talk for a moment about differential heating. Water heats up and cools down slower than land does. Okay, we call this difference differential heating. It's important because it helps moderate the climate in coastal areas. All right, so here's a little bit of an explanation of why land heats up and cools down slower than the water, let me rethink for a second. Water heats up and cools down slower than land does, okay? All right, land does not circulate the way water does, okay? So the surface of the Earth is going to get hotter quicker than the water does, and it's going to cool off quicker than the water does, okay? So the Earth is not circulating. You'll know this if you ever go outside, even on a hot day. If the ground felt warm, you don't have to dig very far before the soil is going to feel kind of cool down in there. So you don't have this, the energy being, transferred down to the deeper parts of the soil. On the other hand, with the water, it circulates. We've talked already about convection a little bit, and we've talked about density, right? The warmer, less dense water is going to rise to the surface, while the cooler, more dense water is going to sink below, and it just keeps going in a pattern, okay? That's why a lot of times you might go to the beach in the early summer. You might go in late spring or early summer, and it's already very hot outside, all right? But then the water is really cold feeling, okay? It just hasn't heated up yet. It hasn't had the time to heat up yet. The opposite can happen if you go to the beach in the fall. It can already be getting kind of cold outside, but the water's still kind of warm compared to how it's going to be in the winter. It simply heats up and cools down slower than land does. And this is something we're going to go into a lot more detail when we get to ocean currents. We're going to be talking a lot more about how the ocean currents and the differential heating between land and water help moderate our climates across the world and help the coastal areas be a bit more moderate in climate than areas that are farther inland. All right, so now let's talk about our second type of energy transfer, conduction. All right, conduction does require a medium. Okay, the energy and heat has to have something to flow through. Okay, with conduction, this transfer of energy and heat occurs when molecules touch each other. Okay, all right, so we're talking now about how energy from the sun reaches the earth and then how it gets circulated about the earth. Okay, so we said already the electromagnetic energy reaches earth through radiation. Okay, the energy waves, the electromagnetic waves, just travel through open space and arrive at earth. Okay, and we said that about 51% of that incoming solar radiation is absorbed at Earth's surface. Okay, so now let's talk about what happens next. All right, the next thing that happens is air molecules touch Earth's surface. Okay, so now conduction is taking place. Okay, and the Earth's surface and the air molecules are the medium for this transfer of energy between the land and the air. Okay, so the surface of the earth is heated by the radiation striking Earth's surface. Then the air of our atmosphere is heated when that air touches the Earth's surface and is warmed through conduction. Okay, and then we've said already in class, all right, hot air rises, right? So when that air gets heated by Earth's surface, it begins to rise, and this leads us to our next type of energy transfer that further circulates the sun's energy around our planet through the atmosphere, and that's convection. Again, with convection, you need a medium, okay? And in this case, the medium is going to be the air, okay? All right, the warmer air rises, okay? But once it gets high up enough in the atmosphere, it cools a little bit, and then it sinks, okay? And this happens again and again and causes a convection current. It's an ongoing thing. The hotter, less dense air is going to rise, while the cooler, more dense air is going to sink, okay? That cooler air, when it comes in contact with Earth's surface again, it's going to get heated again. Its density is going to go down. It's going to become lighter than the air around it, and it's going to rise, okay? Meanwhile, up here, some of that warmer air gets cooler, its density increases, and it sinks, okay? So, in this case, the air is the medium. Now, of course, like we've talked about before, this can happen with water too, okay? All right, warmer water is going to rise, while cooler water is going to sink. All right, so again, just to recap, this is how energy from the sun reaches the earth and then is distributed about the earth or around the earth via the atmosphere. First, electromagnetic energy moves from the sun through open space towards the earth. About 51% of that energy is absorbed at Earth's surface. The air touches Earth's surface, and the air is heated by conduction. Then as the warmed air rises and the cooler air sinks, we get a convection current, and these convection currents further distribute the heat and energy through Earth's atmosphere. All right, let's talk about energy for photosynthesis, okay? In the last lesson, I said that the sun is the ultimate source of energy for Earth, okay? Now, that's particularly true for the living things on Earth, okay? All the energy that your body is currently using right now actually came from the sun, and this is how, okay? So the solar energy strikes the leaves of plants, right? And then the leaves of plants, the plant cells perform this process called photosynthesis, by which they transform that solar energy into chemical energy that the plant uses for food. And that when we eat plants or animals eat plants, we're also using for food, right? Okay, so photosynthesis occurs in plants, algae, and some bacteria, okay? For this chemical reaction to occur, all right, there must be water, carbon dioxide, and adequate sunlight. Okay? And this is how solar energy, that pure energy from the sun, is transformed into chemical energy that then the rest of us living things live off of and benefit from.